Mascouda City Park UAS Mapping Project, Avatar Presenter Script, Slide 1, Title. Good afternoon, my name is Paul Bujak, and on behalf of the operational scientist, I am pleased to present the complete findings from the April 2026 UAS Photogrammetric Mapping and Stormwater Infrastructure Assessment conducted at Mascouda City Park here in St. Clair County, Illinois. This briefing will walk you through how the project was authorized and planned, how the flights were executed, what the data looks like, and most importantly, what we found and what the city should do about it. Let's get started. Slide 2, Project Overview. The City of Mascouda commissioned this project for 3 specific reasons. First, the existing geospatial baseline for the park was built on a 2014 paper survey, more than a decade old and insufficient for current engineering and planning work. Second, the city needed accurate stormwater data to support drainage compliance. Third, an ADA pathway assessment was overdue as part of the city's transition plan obligations. We responded with a 2-sortie autonomous UAS mission covering 45 acres of parkland and adjacent right-of-way. We captured 421 images, achieved a ground sample distance of 1.5 centimeters per pixel, and hit a horizontal accuracy of plus or minus 2.1 centimeters, that is centimeter level precision, not foot level. This dataset replaces what would have required 6 to 8 weeks of conventional survey work. We completed field operations in 2 days. Slide 3, Study Area and Airspace. A word on where Mascouda sits from an airspace perspective. The park is located 8 miles west of Scott Air Force Base, which means we are operating in proximity to Class D controlled airspace. We coordinated all operations through LA&C, the Low Altitude Authorization and Notification Capability System, and received approval prior to any flight activity. No temporary flight restrictions were active during our operational window. The aircraft broadcast continuous remote ID throughout both missions in compliance with 14 CFR Part 89. We also completed a specific operations risk assessment prior to flight. The site was classified Ground Risk Class 2, sparsely populated, which is appropriate for a municipal park setting. All crew briefings, pre-flight checklists, lost link procedures, and contingency plans were documented and executed before the first aircraft lifted off. Slide 4, Flight Planning and Mission Execution. The 2 sorties were designed to serve different but complementary purposes. Sortie 1 used a double grid nadir pattern at 120 meters above ground level with 80% front overlap and 70% side overlap. That pattern gives us complete redundant coverage of the full 45 acres with no data gaps. We captured 312 images over 24 minutes and 38 seconds using the DJI Matrice 350 RTK with the Zenmuse P 135mm lens. Sortie 2 dropped to 80 meters and shifted to a 45-degree oblique configuration combined with low-altitude corridor strips along the detention basin perimeter and storm inlet network. That approach gives us the 3-dimensional geometry we need to assess structural condition on drainage assets. You cannot evaluate a storm inlet's condition from a nadir photograph. We captured 109 images in 18 minutes 14 seconds using the 50mm lens. RTK correction was provided throughout both missions by a DJI D-RTK-2 base station placed on a surveyed control point within the park. 6 ground control points were established using a Leica GS-18T GNSS receiver and verified against 4 independent checkpoints that were withheld from the bundle adjustment for accuracy verification. Slide 5, Raw Data and Metadata. Let me show you what the raw data actually looks like, because the quality of the embedded metadata is what makes this dataset defensible for engineering use. Every one of the 421 images carries a complete EXIF metadata record that includes UTC timestamp to the millisecond, RTK corrected latitude and longitude, GPS altitude in both mean sea level and above ground level terms, positional error estimates in both horizontal and vertical axes, gimbal pitch and yaw, camera model, focal length, aperture, ISO, shutter speed, and image dimensions. For reference, image DJI_0187.dng was captured on April 14, 2026 at 13 hours 42 minutes 17.341 seconds UTC. Position 38.5808312 degrees north, 89.792380 degrees west. RTK fixed status fixed, 6 of 6 satellites used. Altitude 246.312 meters mean sea level, 120 meters above ground. Horizontal positional error, plus or minus 1.8 centimeters. Vertical, plus or minus 3.1 centimeters. Gimbal pitch, negative 90 degrees nadir. Shutter, 1/1250 of a second at f5.6 ISO 100. That level of metadata precision is what allows Pix4D to build a centimeter accurate model without needing to guess at camera position. the RTK system does the work that ground control alone used to require. The complete raw data archive totals approximately 35.6 gigabytes and includes the DNG files, JPEG previews, UGCS mission files, and telemetry CSVs, the DRTK-2 RINEX base station observation data in RINEX 3.03 format, the GCP and checkpoint survey file, the full Pix4D project archive, and ISO 19115 compliant metadata records for each delivered product. Slide 6. Processing and quality. All imagery was processed in Pix4D Mapper version 4.8 using the three-dimensional maps template with high point cloud density enabled. Processing ran on a workstation with 32 processing cores, 128 gigabytes of RAM, and an NVIDIA RTX 4090 GPU. Total processing time for the 421 image dataset was 4 hours 22 minutes. The quality results are strong across every metric, 100% of images calibrated. RMS reprojection error of 0.28 pixels, well below the 1 pixel threshold for a quality result. GCP horizontal RMSE 2.1 centimeters CE90. GCP vertical RMSE 3.4 centimeters LE90. Independent checkpoint RMSE came in at 2.6 centimeters horizontal and 4.1 centimeters vertical, confirming the GCP results were not overfitted. The dense point cloud contains 82.4 million points at a density of 820 points per square meter. Camera model was fully optimized. These results meet ASPR's Class 1 positional accuracy standards at this ground sample distance. Slide 7. Final products. 6 final products are delivered as part of this project. The OrthoMosaic is a true color GeoTIFF at 1.5 centimeters per pixel, 4.2 gigabytes in full resolution with a 280 megabyte cloud-optimized version for web delivery. The digital surface model captures all above-ground features at 3 centimeters per pixel. The digital terrain model is a bare earth product at 5 centimeters per pixel, derived through ground classification of the dense point cloud. This is your primary input for drainage modeling and ADA slope analysis. The classified point cloud is delivered in LAZ compressed format at 82.4 million points. The stormwater infrastructure inventory contains 34 cataloged assets with RTK accurate coordinates, condition ratings, and photo references in both GeoJSON and shapefile format. And finally, the accuracy and quality report documents every GCP and checkpoint residual in both PDF and CSV format. All products are delivered in NAD83 Illinois East Coordinate Reference System, EPSG 3435, with NAVD88 vertical datum, ready for direct import into ArcGIS Online or any standard GIS environment. Slide 8. Key findings. Now to the findings that matter most for the city's planning and budgeting decisions. 3 storm inlets are rated critical condition and require action before the 2026 storm season. Asset E03 has a partially collapsed inlet grate with standing sediment accumulation. Asset E11 shows severe undermining at the head wall with a visible void formation. This is a structural failure in progress. Asset E28 has separation between the inlet pipe and the structure wall with surface settlement already visible above ground. Any one of these 3 failing during a significant storm event creates risk of pavement undermining and flood control system bypass. We are recommending immediate remediation and cost estimates ranging from approximately $4,200 for the head wall repair to $12,800 for the pipe reconnection and surface restoration are included in the technical report. The detention basin is operating at 88% of design capacity. Our DTM-derived volumetric analysis shows current storage at 1.24 acre-feet against a design capacity of 1.41 acre-feet. The deficit is attributable to approximately 0.17 acre-feet, about 185 cubic yards of accumulated sediment. We are recommending you submit this analysis to the Illinois Department of Natural Resources Division of Water Resources for review under your existing NPDES permit and commission sediment removal within the next 12 months. Budget range for dredging and disposal is $28,000 to $42,000, depending on disposal requirements. 2 ADA pathway segments are non-compliant under PROAG Section R3027, which establishes a maximum 2% cross-slope for accessible routes. Segment P04 on the Pavilion Northwest approach runs 42 linear feet at a maximum measured cross-slope of 2.8%. Segment P09, connecting the parking area to the sports field, runs 28 linear feet at 3.1%. 14 other pathway segments totaling 1,847 linear feet were confirmed within tolerance. A corrective action memo and transition plan amendment should be issued within 30 days. Slide 9. Recommendations and close. To summarize the recommended action sequence: immediately repair the 3 critical inlets, submit the basin analysis to IDNR, and issue the ADA corrective action memo. Within 6 to 12 months, commission basin sediment removal. Integrate this dataset into your ArcGIS online environment as the authoritative base layer, and initiate your Parks Master Plan RFQ using what we have delivered as the Site Analysis Foundation. Looking out 1 to 3 years, we recommend establishing an annual UAS reflight program in the April to May window to track asset condition trends over time and measure the sedimentation rate in the basin year over year. Everything you need to act on these recommendations is in the deliverable package: the orthomosaic, the terrain models, the point cloud, the asset inventory, the accuracy report, and the full raw data archive including RINEX base station files and mission telemetry. The operational scientist is available to present these findings directly to City Council and to support the handoff of this dataset into your GIS environment. Thank you for the opportunity to serve the city of Mascouda. This project demonstrates exactly what autonomous UAS operations can deliver when they are executed with rigor, centimeter-accurate data, defensible documentation, and findings that translate directly into capital planning decisions. We look forward to supporting the next phase of this work.